Let's go ahead and pop out the chat. Can everyone hear me okay that is joining us right now? Hopefully we are. Let's go ahead and get all this set up while we wait just a few more minutes. I'll get started around 4:55-ish, depending on how many people wind up joining us today. But let me make sure that everyone can hear me. All right. Should be good to go. I'm going to go ahead and just stop the camera for the first 10 minutes here. And then we'll go ahead and start in about 4 minutes. it's the 55. We'll go ahead and at least start. I think we can get done in a reasonable time. So today's lesson, we're going to be working out of O3 SHAP, O3 class confusion, and O3 research. Now it's going to be a bit of a different lesson because we've kind of gone over all the techniques for training models. Now we're going to focus more on interpretation and sort of how that applies from a research perspective and the sort of pitfalls that you guys should be aware of when doing research. So the first library that we're going to look at is SHAP. And SHAP more or less is a library that lets you interpret neural networks. And we're going to use it specifically for tabular neural networks. So I wrote a library that'll sort of port functionalities over called fastshap. And we're going to sort of walk through what each of the different functionalities do and a little bit into sort of how it works. Now I've made it a pip package, so all you have to do is just pip install fastshap. And the first thing you need to do is actually train a model, because whenever you're doing interpretation, we always need something to look it off of. So we're just going to quickly train an adults model like we've been doing for the last few weeks. And we're going to take a look at sort of how it works and a little bit about its behavior. Now, the first thing I'd like to mention is SHAP doesn't test for exact causality, more so just gives us a window into how the model behaves given certain inputs. So those are two very different things. So when you're using fastshap, you're going to want to import the interpretability module, which is fastshap.interp. And anytime you want to use it, you're going to make a SHAP interpretation object. You do so by passing in your learner along with some rows of data to use. Now this can, if you don't pass anything in, it'll automatically take a few samples off of your validation data set. This is if we want a test data set of some form. If you want to look at a single row, or that's all that the test data you have that you particularly care about looking at, you can do so by passing it in this form. So if I say wanted just row 20, I'd do 20 to 21 here, and it would just pass in row 20. And what this essentially does is SHAP will in the background run its interpretability modules and set everything up. This SHAP operates essentially by having what are called SHAP values. Kind of think of them similar in the sense to the values that we got from permutation importance. You can read into more about how they're particularly calculated. Just know that they're a method of measurement, specifically for SHAP. Also, we're going to be looking at decision plots, dependency plots, force plots, the summary plot, and the waterfall plot today. This is all that I've sort of brought over for us to look at. Let me make sure that I don't accidentally have my microphone on. Good, I don't. And these are sort of all that I've brought over for us to look at and use, and it should be a pretty good. It's got most of the abilities of native SHAP. So let's take a look at the 10th row of our data frame here. We can see that we've got an age, our work class, and we have the ground truth answer of less than $50,000. Now, I want to see sort of how each of these variables affected my model's decision into getting to this negative 50K or to positive 50K, and sort of see how each particular value shifted the decision. That's what decision plot will allow us to do. Now, each of these are our transformed values, so this is after it's gone through all the pre-processing. And we can see if we pass in class ID of 0 and a row index, we can see that the model goes, oh, okay, we're using a classification model, and we're going to be looking at the scores for less than $50,000. Now, if we want to use let me make sure we can still hear me. Cool. If we want to use a different class, I could specify class ID as 1, which we'll see in a moment. And it'll tell us what row we're looking at. So here I can see that I'm looking at what affects the negative 50K. And from left to right, essentially here, we can read it as the more in the red we are, the more we are in tuned for less than 50K. The more blue we are, uh, the more inclined we are to greater than or equal to $50,000. And so we can see how each of these values sort of drew our model in. And then if we look at it the other way around, which is greater than or equal to 50K, and we wanted to see our model's particular output for that answer, we can look at how each variable was affecting and essentially tuning the output into getting that particular probability. Because remember, we could always do, learn.predict df.iloc, and we were looking at the 10th one. And what it'll give us is these two probabilities here after they've sort of gone through an argmax and a softmax. But what SHAP then lets us do is say, okay, before we, did the whole softmax to Rmax and we had just the raw values, how were they being predicted and what was the model looking at? So this is the first way that we can get an in-depth look into any model's decision, especially in Tabular, or specifically for Tabular. We don't have this ported for Vision, and that's mostly because the native fastai vision techniques work pretty good. And SHAP doesn't really add anything to it. Now, the next bit we're going to look at is dependency plots. Now, dependency plots essentially operate by plotting our age, for instance, on one axis, and then relationship here, for instance, on the other axis. And we can see the relationship from each of these two variables when they're together. So we can look at, say, clustering. So when my relationship's high and my age is high, how does that affect the data? Like, what does it look like, essentially? How does it relate to the model? And so here we can pass in when I have the first class, which was our less than 50K, and I plot a dependency plot of age. What is my model most correlated with, and what does that look like? And so here, it's marital status when I ran it again. And so we can see as, our age values sort of decrease, how does that in turn get affected by the marital status? So if we look at it again, we should have the exact opposite. So if you want to read more into dependency plots, I'd highly recommend reading a few articles because dependency plots are valuable, and I'm still trying to understand them a little bit. But it's here, you can use it, and we'll sort of talk more in research as to how best to go about these techniques from a research perspective and why it's important to have explainability. So the next bit we'll look at is force plots. And this allows us to sort of look at how each variable affected the model at a specific value for a particular class. So like here I can run the force plot for greater than 50K, and I can do, say, age, and look at how age affects education. And I can look at the number of affected samples and see how particular age values affected what the predictions were. And I haven't played around with this part too much, but you can look at essentially any variable, even the model's output, for instance, and we can look at how it affected each of the outputs themselves. We could put like age and look at sort of what variable range of age affected the model's particular guesstimation here. So it's a really neat way to sort of further look into your model's behavior outside of fastai. Next, we'll look at summary plots, which this should look very familiar to us. It's kind of similar to feature importance, so we can see sort of how each variable had an overall weight on top of a relative importance towards each outcome. So we can see that, marital status was the second most important variable, and in general, it had a higher impact on less than 50K, whereas age was one of my the most important variable, and it mostly affected greater than or equal to 50K. So it's sort of a higher in-depth look into permutation importance. I'd recommend both and pay attention to if they're a little bit differently and a little bit different, and probably try and figure out why they might be different, but in general they shouldn't be. And then sort of the last plot we're going to look at is waterfall plots. And it'll, in a pretty visualization, explain one row's predictions and sort of how each variable affected and pulled the outcome. Now, this is similar to the decision plot, but I like it a lot more because it's a lot more visually appealing. So here we can see we pass in our row index, our class ID, which as you can see can be a string. So I'll say less than 50K on our 10th row. And we can look at how each of the variables sort of pulled our outcome here into our proper answer. We can look at so we can see that age brought it more towards the right answer, but our education number and our education both sort of pulled it in the opposite direction. And then the sum of all of these values should, I believe, equal to what the sort of f of x is. Yeah, the force plots and all of these plots, honestly, I love this library just because it's very easy and understandable to interpret. And so we can use the waterfall plot to instead look at the same row and pass in, a different class. So now we'll look at sort of what happens if I want to look particularly greater than or equal to 50K. And then we can look at, the age, the education number, and see how it affected it in the opposite direction. Kieran asked, how would the summary plot look if we had multi-class? I don't believe that I've ported multi-class over. This was in collaboration with another user, and I don't think we looked at multi-class classification yet. You can try it if you have a multi-class tabular dataset, and we can take a look at it and debug it in the forums. But I personally haven't tested this with multi-class, so I don't quite have an answer to your question there. But I will say this supports more than just binary. I know all the examples are binary, but it supports binary along with regression, multiple classes besides that, along with regression. Are there any more questions related to SHAP specifically? All right, if there's not, and as there's a little bit of lag, I'll pay attention to the chat. We'll go ahead and move on to class confusion. So class confusion is something that I made back in fastai version 1 when I first started looking at tabular data. and I brought it over to version 2 just because I loved it so much. Essentially, what it allows us to do is sort of similar. Yes, fastshap is using the SHAP library internally, and essentially what I've done is built a wrapper around it. So this is all natively the fastshap library. If you go look at the source code, it will also show this, and you can sort of look at what I did to port it over, or what we did, sorry. Now on to class confusion. So class confusion is native fastai, and the goal behind it is sort of similar to image cleaner in a way, where it allows you to get an insight into how your model behaved, specifically when it got things wrong. So, first we have the sort of confusion matrix where we're given a grid sample and, we have 30 values, for instance, were missed in this class and 40 values were missed in this class. But that's about all we got. And I wanted a deeper look into what was going on with these confused classes. And so that's where the idea of class confusion came from. So just like before, we're going to want to train a tabular model. This should support images. I did a very quick port, so I need to double check, but it should. Now, does it support multi-class classification? I don't believe it supports regression either, mostly because that gets a little bit more complicated internally, but it is something that I'm looking to do. So after we've trained our model, we'll go ahead and build an instance of class confusion. In the instance of tabular, you can pass in any variables you want to look at, along with any test data, and if we want to pass in a list of ordered classes. So what I mean by this is, so like I can pass in negative 50k and positive 50k here, or less than 50,000 or more than 50,000. But I could also say do something like so, where I pass in a list of ordered classes, and all I do is just reverse this order. And then I would pass this class list into class confusion and specify ordered as true. Otherwise, it'll grab all the combinations for the list of classes that are available to what you sort of passed in to look at. Now, what that equivocates to is I'm greater than 50k, and when the answer was greater than 50k, and I guessed less than 50k. So it's not looking at when I got the right answers, only when I got the wrong answers. And then optionally, you can pass in a test data loader of variables. Otherwise, it'll use your validation set. So here I'm just going to pass in my data loader, my list of classes, and it'll pop open this sort of widget view here. Now, this currently in version 2 is only supported for the Colab environment. I'm working on porting it over to just regular Jupyter. But for instance, I want to look at how the work class distribution of my misses was different from the original distribution. Sort of, I can see where it gives me an insight into what was confusing my model the most. And so if we look at the original distribution, so we have like, mostly private, self-employed, local government, so on and so forth. And then the question mark is our missing values. And then if I look at what sort of confused the less than 50k, I can see that it mostly was people from the private sector, with a little bit from the local government, and then if my values were missing. Whereas the other way around, it was again mostly private sector, self-employed, local government, and self-employed but not incorporated. So it really lets you sort of see, okay, based on my class distribution here, do I need to do maybe oversampling? Here might be a good case because I'm noticing, okay, when it's, when the right answer is greater than or equal to 50k, and I'm confusing it, some of the instances that are affecting it is like the self-employed not incorporated. Or actually, what has a greater impact is the self-employed that are incorporated. And if we track that back to the original distribution, we can see that there's not that many samples. There's about 12 samples in our particular data loader here of the first 100 rows. So I might want to train more with our self-employed incorporated class in this instance to try and make that a little better. So you can sort of see how to interpret this. So like this is shown for, education, marital status, occupation, relationship. If I don't pass in a set of variables here, it'll just automatically use all the variables available to it. Just be careful whenever your model has like, 100 different variables, you might want to pass in a variable list to use. Now this was for the categorical variables. If we go over and look at the continuous variables though, it shows a very different type of plot. This is just a typical distribution plot. And so here we can kind of see what the bell curve looks like originally. And then as we change it, sort of what those values are. And all of them follow the same axis, so we can just read this straight in terms of an x-axis. So here we have the original, 20, 30, 40, 50, 60. We could see that when we were confusing the less than 50K, most of it was coming from everyone around the 30 to 40 range, and the other way around was around the mid 40s to the mid to low 50s. So we can sort of get a general idea of how each variable was affecting my model's ability to predict the right answer. I found some uses in this when trying to explain ideas to people who don't know exactly what a neural network is and don't know sort of how to do these types of models. And everything is best explained with a pretty chart rather than a line of code that says, "Hey, I trained," and I got this percent accuracy. And that's sort of a good lead into the final topic. It's going to be a little bit shorter just because there's only so much we can do with Tabular, but to me, these are important ideas and concepts to hit. There's other interpretation libraries that are also good, that if we can bring into FastAI can really help empower researchers in sort of getting past the black box argument. And so, if you know of a few and you want to bring them in, I highly encourage you work on that because it's needed. Yeah, we have, the confusion matrixy and the most confused that we can plot, but having the ability to, further dig into it is extremely important from an interpretation standpoint. So, if there's no more questions on either of these two topics, which if there are, go ahead and post them and, we'll backtrack. The last bit I kind of want to touch on is doing research. In this case, it'll be specifically with Tabular, but these sort of ideas and recommendations can be applied most anywhere. This is just sort of what I've seen and what I went through when I did research here at a university where they didn't do research with neural networks. They were still very much affected by it's a black box. Oh, we can't use it for Tabular. It's not built for that application and there are better ways. And so I'm going to go ahead and kind of walk us through a few of the challenges that I faced and sort of how you should take a general approach to doing research. And the first thing is to understand your data. Understanding kind of the behavior of the data, the distributions like we saw with class confusion, before you even start training, what's class A versus class B? how get the most information out of your data that you can before you start training. And then after thoroughly understanding the data, you sort of get a general intuition as to maybe a little bit of the behavior of the model and the behavior you would be expecting. The reason why that's important is, yes, I could just, throw data at my model and say train, and then all of a sudden, like, I get 90%. But, you don't really understand why. You just know that it does. And understanding it from a data perspective and from a technique perspective allows you to merge the two ideas together into something that you can then, relay with confidence instead of just a quick tidbit of, I plugged something in, it worked, I don't know why, but it worked. And that sort of brings us on to the next idea, which is understanding the techniques. So at my school, I was sort of the first one to bring in the idea of tabular neural networks. And so I was the expert on the team. And so, I had to communicate with the professors, sort of how it all worked. I had to communicate with my team members how it all worked. And what that forces you to do is make sure that you know what you're talking about. Because they're using you as their primary source of sort of understanding how all this works. Because in a perfect world, you would hope that the professors and your fellow researchers would look into it. But at the end of the day, you've been doing tabular neural networks probably for longer than they have. So they'll look into it, but you understand sort of the behavior a little bit because you've been playing with these models for, however long you've been doing fastai, if you've been wanting to focus your research on it. And so it's important that you make sure that what you're telling your team is accurate and reliable information. I found this a struggle because, you know, while Jeremy goes over sort of, how the neural networks kind of work a little bit, especially with tabular, we don't get too much insight into it. Maybe this will change in the new course because there is there's a chapter on tabular that goes into a large amount of detail, sort of similar to what I've been trying to do here. And so I think that will change, but that doesn't mean that you should just, you know, solely go off of what Jeremy says alone. Um, you should also go look into, how it all works in the background. The tabular neural networks that we use were based on a particular set of papers. And so reading sort of what those papers are can help explain the ideas and the concepts to other people. Like our um, our embedding matrix and sort of the ideas behind it came from NLP. And so being able to understand first how the technique worked in natural language processing and then bring it over to how the embeddings can help us here is super important because otherwise they're just going to say, well, what's the difference between using, random forest here versus a neural network? The embeddings is why that's different. And so it's important to understand, the techniques that you're applying and why they work and how they work. Along with this is test sets. Test sets, when it comes to tabular data, are extremely important because most of the time when you're working, whether it's time series or otherwise, people are not only going to want to know how you performed on the data set, but how you can forecast. What's your model's behavior on something it's never seen before? And so this is very important to think about whenever you're building your data. If it's time series and you have multiple inputs, you should probably split your data at those multiple inputs on a time series perspective. And so it gets a little bit more complicated, but in the long run, that'll be worth it rather than taking the easy way out, which is, just split by random percent, which is the wrong approach to do it. I've also included a link to Rachel's How and Why to Create a Good Validation Set. It's from 2017, but it tells you everything you should know about why, split by random percent might not necessarily be the best approach. And also in general, I always have a third test set when it comes to working with my research data. That way I can understand not just from training, but from inference how the model sort of behaves and how it does. And this also then, goes back to class confusion and SHAP and why I have, the option to work with a test data loader. Because let's say I run this on my validation data. Let's think about what that tells me. Okay, that tells me when my model was training, what it was looking at, which is great. That's fine. That tells me, why I got to 90%. But from a deployment perspective, I want to be interested in how my model works on unseen data, data it's never looked at before. And sort of what does each variable do in that exact situation? Because I can guarantee you these plots will look very different on data that the model has never seen before. And so there's two different behaviors that you have to watch out for. And sort of that's why it's important to have this test set and understand how to build a test set in your given data set. And test sets don't have to be unlabeled. Kaggle has that, but at the end of the day, Kaggle does have labeled test sets, just we don't get to see those labels. So along with that, it's important to understand, you know, how the techniques work as well as just understanding, what they do, sort of how to use them. For instance, uh, you know, again, neural networks are sort of seen as a black box. And, so many researchers will say, well, we don't know how it works. We can't do feature importance on a neural network because the layer has, 200 neurons and you have another layer that has 100 neurons. And that's, I can't map that easily. No, you can't. But we can get a general idea and sort of overall look into how the variable might have affected it. There can be sort of a chain, a chain effect of affecting X variable and it affected, Y, Z, and A variables. But that's okay because we just want to get a general understanding. If you go present this to your boss, they're not going to ask specifically, tell me every little detail about how the model works. They're going to want to know, does it work? And where could the possible biases come into play? And so that's, in general, where these tools sort of and their ideas sort of came from. We can understand what class confusion and SHAP is doing in the background. We can go look at the code for class confusion and you can see sort of, what I was doing, how I got those results. But it's another set of skills entirely to communicate that effectively. SHAP and class confusion are the tools to help you to build sort of plots and intuitions that you can then, explain to someone that might not know, what a neural network is exactly, but I can show them, these distribution plots, and they'll know exactly how my model is sort of predicting and possibly an insight into the approach it's looking at. Because a lot of times the data can explain these sort of distributions in a way. And that's exactly how I've built class confusion. Look at the data, look at the model, and it'll tell you a story of how it's behaving. And then probably the most important rule and idea that I've sort of figured out when going through all of this, because I was the only one that was doing neural network research on Tabular at the school, so I didn't have, a Jeremy as a mentor where I could just, automatically go, hey, tell me your thoughts. Am I doing this approach correctly? I didn't have that, because it is neural networks. And no one had looked at that approach yet. And so if you're, in general, sort of how I approached that problem was if I was iffy about any concept, any idea, and I knew I couldn't explain that to someone who didn't know, what a neural network was, then I automatically just went, okay, I need to understand more about how this works and in probably a bit more depth. That way I understand how to bring it down a level from, a high level to a low level understanding and still get the same point across. This is a problem that I had with my research projects because, they all used random forest. And so I had to figure out sort of first how to get them to understand that it's not that the FastAI library itself is doing something, it's the neural network and then the FastAI models or the FastAI framework training these PyTorch models. And probably the hardest thing I had to experience was also admitting when you're wrong. Admit, hey, I rushed something in the beginning, and while it got good results, they were the wrong results. I didn't take into account maybe class imbalances. And so while I was getting, 90% on this data set, which turns out was really good, it was because only like 5% of the data was this other class. And so there's this humongous class imbalance issue. And if I go and publish that, without thinking about this, then I'll be ripped to shreds because, my mentor didn't catch it, I didn't catch it, and it was the wrong approach to do so. And, so then you got to sort of backtrack and go, okay, well, that's why I got most of these answers right. We can't publish that because I need to go back and redo my work. Otherwise, even if it does, let's say, get published and even the reviewers miss it, well, now I'm telling people that, hey, I got 90%, when in reality, I might have been doing really, really poorly on the actual class that we should have been paying attention to. And so it's important for you to sort of have this idea of self accountability and self reliability when working through this because, neural networks, they're kind of new in the sense that they're more accessible. And we don't want to get people off to the wrong track and off the wrong foot when performing research when there's not a lot of research done in this area, specifically with Tabular, because otherwise this will just have, a chain effect of issues down the road. So I guess that's sort of, I guess you could call it a tangent, you could call it a rant, but just sort of a few ideas and a few points I wanted to make about doing research that aren't really talked about a whole lot, and they're mostly figured out through experience. But if I had to sort of sum it up in just, 5 points, understand your data and the behaviors that are already in there before you train the model. Understand sort of the techniques and a little bit more depth than just what the lectures go into, especially with Tabular. That way, you know the behavior and sort of get an insight into it. Understand how to interpret our models and the different libraries you can use and what each of them specifically explains, and more importantly, what it doesn't explain. I mentioned earlier that SHAP doesn't do correlations. It doesn't have a causational, sorry, not correlation, doesn't have a causational impact entirely, and SHAP's documentation will say this. And so it's very important to make sure you're using the right terminologies. And then finally, just, keeping yourself accountable. You are your only source here, essentially, for what is good, what is right, and what is not, because you have access to your data that you're looking at, and maybe no one else does. And so you're the last line of defense in making sure that you've done something right. But besides that, that's sort of all I have for the class today. Next week, we're going to look into implementing different ideas and different models into the framework, as there are some neural network models for Tabular that have come out in the last year or two, and they're interesting. certainly, and so there's something that we should look at. But after that, I believe that's mostly it for the tabular module. So afterwards, we'll probably take a week after whatever the last lesson for tabular is and start on natural language processing. But thank you guys very much for joining me today. And please do, stay safe, social distance, extremely important. And I will see everyone next week.